Hello everyone, today I'm going to take you on a journey to the very edge of space and time to look closely at what the James Webb Space Telescope saw that made scientists go entirely silent. Before we begin, don't forget to subscribe to the channel and support future videos. And now, without wasting any more time, let's explore the quiet depths of the cosmos and the profound revelations waiting for us in the dark. There is a specific kind of silence that exists only in the vast empty spaces between the stars. It is not an empty silence, but a heavy, expectant one. It is the silence of an ancient universe keeping its secrets, waiting patiently for someone to look closely enough to understand them. For thousands of years, we looked up from our small blue world with nothing but our bare eyes, gathering whatever fragments of starlight managed to pierce through our thick atmosphere. We built towers, we ground glass into lenses, we sent metal tubes into low Earth orbit, all to capture a little more of that ancient light. But there were places we could not see. There were times, buried deep in the history of the cosmos, that remained completely hidden behind thick veils of cosmic dust and the relentless stretching of space itself. To see into these hidden places, we needed a different kind of eye. We needed a mirror that could catch the faint, invisible heat of the universe's first moments. We needed the James Webb Space Telescope. When the first true images from this golden observatory finally arrived on Earth, the reaction within the scientific community was not immediately one of loud celebration. Instead, there was a profound, almost reverent hush. The data came down in streams of numbers, translated into pixels, and as the screens illuminated the dark rooms of control centers and university offices around the world, the people who had spent their entire lives studying the sky simply stopped speaking. What they saw in those first few moments fundamentally challenged everything they thought they knew about the beginning of everything. To understand why they went silent, we must first understand the journey of the telescope itself and the extraordinary nature of the light it was built to capture. The James Webb Space Telescope does not rest in the comfortable vicinity of our planet. Unlike its predecessor, the Hubble Space Telescope, which circles just above our atmosphere, Webb had to travel much further. It sits 1 million miles away, resting in a delicate gravitational pocket known as Lagrange Point 2. Out here, far beyond the orbit of the Moon, the telescope is held in a gentle balance between the gravitational pull of the Earth and the Sun. It needs to be this far away for a very specific reason: the cold. The telescope is designed to see infrared light. Infrared light is essentially heat. Every star, every galaxy, every planet, and even the telescope itself emits heat. If the telescope were warm, its own heat would completely blind its senses, like trying to see a single firefly while standing directly in front of a massive, blazing bonfire. To see the faintest, oldest sources of heat in the universe, the telescope must be unimaginably cold. It is protected by a sun shield the size of a tennis court, made of 5 layers of a material called kapton. This shield is gossamer thin, yet it performs a miracle of thermodynamics. On the side facing the Sun and the Earth, the temperature boils at over 200 degrees Fahrenheit. But step behind the shield to the dark side where the golden mirrors rest, and the temperature plummets to nearly -400 degrees Fahrenheit. It is a realm of near absolute zero, a frozen stillness where the telescope's sensors can finally quiet down enough to listen to the whispers of deep space. The mirrors themselves are a marvel of quiet engineering. There are 18 hexagonal segments made of beryllium, a metal chosen because it holds its shape perfectly in extreme cold. But beryllium alone is not enough to catch the light we seek. The surface of these mirrors is coated in a microscopic layer of pure gold. Gold is highly reflective to infrared light. It catches those long, gentle waves of heat and bounces them into the secondary mirror, then down into the instruments that wait in the dark. Imagine a single particle of light, a photon. Imagine it being born in the fiery heart of a massive star, just a few 100 million years after the Big Bang. When it first bursts forth into the dark, it is a brilliant, energetic particle of blue or ultraviolet light. It leaves its home galaxy and begins a journey across the void. But the universe is not static, it is expanding. And as this photon travels for 1,000,000 years, then 1,000,000,000 years, then 10 billion years, the very fabric of space beneath it stretches. As space stretches, the light wave is pulled along with it. Its wavelength grows longer, its energy softens. By the time it has traveled 13 billion years, it is no longer visible to human eyes. It has stretched so much that it has fallen off the visible spectrum entirely, turning into a long, quiet wave of infrared light. This process is called cosmological redshift. It is the reason the oldest things in the universe are invisible to ordinary telescopes. The light from the first galaxies is still washing over the Earth every single second. But it is a ghostly light, stretched into invisibility by the expansion of time and space. For decades, cosmologists knew this ancient light was out there, passing through us, unseen. They built models, ran simulations, and wrote textbooks about what those first galaxies must look like. They believed that if they could ever build a machine sensitive enough to see that stretched, invisible light, they would find a quiet, simple, early universe. They expected to see tiny, fragile fragments of galaxies, small clumps of stars just beginning to pull themselves together out of the primordial gas. They expected the dawn of time to be a slow, gradual awakening. Then, the golden mirrors aligned. The sun shield blocked the glare of our local star. The instruments cooled to their operating temperatures, and the James Webb Space Telescope opened its eye to a patch of sky that looked completely empty. It gathered light for hours, drinking in the faint infrared photons that had been traveling for more than 13 billion years. When the image was finally processed and displayed on the monitors back on Earth, the room went quiet. They did not see the tiny, fragile fragments they had predicted. They did not see a slow, gradual awakening. They saw a universe that was blazing with massive, fully formed galaxies. They saw structures so vast and so bright that they simply should not have had enough time to exist. The light hitting the sensors was telling a story that contradicted the carefully constructed timeline of the cosmos. The scientists looked at the screens, looked at the data, and realized that the universe was far more mysterious, far more efficient, and far more complex than they had ever dared to imagine. The silence in the room was the sound of a paradigm shifting, of human knowledge reaching its limit and recognizing the profound, humbling vastness of the unknown. To understand the weight of the silence that fell over the astronomical community, we must quietly walk through the timeline of the universe as we understood it before the James Webb Space Telescope opened its golden eye. For nearly a century, we have been piecing together a story called the Standard Model of Cosmology. It is a beautiful, elegant narrative that begins roughly 8 billion years ago with a single, incomprehensible moment of expansion, the Big Bang. After this initial flash, the universe was a violently hot soup of fundamental particles, expanding and cooling. For hundreds of thousands of years, it was too hot even for atoms to form. Light could not travel, it was trapped in a dense fog of ionized plasma. Slowly, gently, the universe expanded enough to cool. Protons and electrons found each other, embracing to form the first atoms of hydrogen and helium. The fog cleared. Light was finally free to travel across the vastness of space. This moment is known as recombination, and it left behind a faint echo of microwave radiation that we can still detect today. But after the fog cleared, the universe entered a period known as the Cosmic Dark Ages. There were no stars, there were no galaxies. There were only vast, silent clouds of hydrogen and helium gas drifting in the expanding dark. Gravity, the quiet architect of the cosmos, went to work. Over millions of years, gravity began to pull these gas clouds together. The denser regions gathered more gas, becoming heavier, pulling more forcefully. Deep within the hearts of these collapsing clouds, the pressure and temperature rose until, finally, nuclear fusion ignited. The first stars blinked into existence, piercing the dark ages with the first starlight. According to our best models, this process was slow. Building a galaxy is a painstaking cosmic endeavor. The first stars were thought to group into small, ragged clusters. These clusters would slowly attract one another, drifting through the dark, merging over hundreds of millions or even billions of years. It takes time for stars to form, burn through their fuel, die in supernova explosions, and scatter heavier elements into the void to form the next generation of stars. Therefore, if we were to look back in time to the very early universe, say, just 300 to 500 million years after the Big Bang, we expected to see a nursery. We expected to see small, disorganized, messy little clumps of blue stars struggling to pull themselves together into the majestic spiral and elliptical galaxies we see in our modern universe today. We thought we understood the pace of cosmic evolution. Then came the data from Webb. When astronomers pointed the telescope at a seemingly empty patch of sky near the Big Dipper, a region known as the extended Groth Strip, they were looking for those tiny infant galaxies. They used the telescope's near-infrared camera to peer through the dust and capture the deeply redshifted light from the edge of time. As the images were processed, distinct red smudges appeared on the screens. These were galaxies, located incredibly far away. By analyzing the spectrum of their light, scientists could measure their redshift, determining exactly how long the light had been traveling. Some of these red smudges existed just 500 million years after the Big Bang. Some were even older. But it was not their age that caused the scientists to fall silent. It was their size. These were not tiny, ragged clumps of newly born stars. These were monsters. The data revealed galaxies that were as massive as our own Milky Way. Our Milky Way took over 10 billion years of slow, steady merging and star formation to reach its current size, holding hundreds of billions of stars. Yet here, in the images from Webb, were galaxies containing tens of billions, perhaps hundreds of billions of stars, sitting calmly in a universe that was only a few 100 million years old. The math did not make sense. It was like walking into a nursery ward and finding fully grown adults sitting in the cribs. These early, massive galaxies were quickly nicknamed universe breakers. Their very existence seemed to violate the fundamental speed limits of cosmic evolution. How could so much gas collapse so quickly? How could so many stars ignite in such a short fraction of cosmic time? There simply had not been enough time, according to the Standard Model, for gravity to sweep up that much matter and organize it into such vast, dense structures. The silence that followed this discovery was a mixture of shock, awe, and deep intellectual humility. When a scientist encounters data that perfectly matches their prediction, there is a quiet nod of satisfaction. But when a scientist encounters data that completely breaks their model, there is a profound, breathless stillness. It is the realization that the universe is not bound by our equations. The universe simply is, and it is far more capable, far more dynamic than we had presumed. Researchers double-checked their calibrations. They reran the software that interpreted the infrared data. They checked for errors in the way the redshift was being calculated. Perhaps the galaxies were closer than they appeared, shrouded in an unusual type of dust that mimicked the redshift of extreme distance. But as more observations were made and the data was scrutinized by independent teams across the globe, the reality settled in. The calibration was correct. The distances were accurate. The universe breakers were real. To make matters even more perplexing, these early galaxies were not just massive, they were mature. Some of them showed signs of having smooth, organized structures, much like the majestic spiral galaxies of the modern era. This implied that they had not only formed incredibly fast, but had also settled into a stable rotation in a fraction of the time we thought necessary. Furthermore, the light from some of these galaxies revealed the presence of heavier elements like carbon, oxygen, and dust. In the early universe, there should only be hydrogen and helium. Heavy elements are forged in the hearts of stars and scattered when those stars die. To see heavy elements so early means that entire generations of stars had already lived, burned, and died in spectacular supernovae, enriching the galactic gas, all within the first few 100 million years of time. The speed of this stellar life cycle was breathtaking. It painted a picture of an early universe that was not a quiet, slow awakening, but a violent, hyper-efficient forge of creation. Gas must have poured into these early dark matter halos at astonishing rates. Star formation must have occurred with a ferocity we have never witnessed in our local modern universe. As the quiet awe in the control rooms turned into a flurry of new hypotheses and gentle debates, scientists realized that they were not just looking at a few outlier galaxies. They were looking at a fundamental gap in human knowledge. The James Webb Space Telescope had done exactly what it was built to do. It had pulled back the curtain on the unknown. And what it revealed was a cosmos that refused to fit neatly into the boxes we had drawn for it. The silence of the scientists was a sign of respect. It was the quiet acknowledgement that we are still beginners in understanding the grand architecture of reality. The universe breakers challenged our assumptions, forcing us to return to the chalkboard, to rethink the nature of dark matter, the behavior of primordial gas, and the very dawn of light itself. And as the golden mirror continued to gather the ancient heat from the edge of time, we could only wait, watching the quiet dark, wondering what other impossible things were hiding in the deep. To comprehend how such massive, mature galaxies could exist so early in the timeline of the cosmos, we must look beyond the light. We must look at what we cannot see. The visible universe, the shimmering stars, the glowing nebulas, the sweeping spiral arms of galaxies, makes up only a tiny fraction of what is actually out there. The vast majority of the universe's mass is completely invisible to us. It does not emit light. It does not reflect light. It does not block light. It only interacts with the rest of the universe through the gentle, persistent pull of gravity. We call this mysterious substance, dark matter. While the name might sound ominous, dark matter is not a destructive force. In fact, it is the quiet architect of everything we see. It is the invisible scaffolding upon which the visible universe is built. Without it, the galaxies would fly apart, their stars scattering into the void like dust in the wind. Without it, the early universe would have never been able to pull enough gas together to form the first stars. Astronomers believe that dark matter forms a vast, intricate structure across the entire universe, a structure known as the cosmic web. Imagine a three-dimensional spider web stretching across billions of light years. The threads of this web are massive, invisible filaments of dark matter. Where these filaments intersect, they form dense, powerful nodes. In the quiet, expanding dark of the early universe, these dark matter nodes acted as profound gravitational wells. They were traps for the drifting clouds of primordial hydrogen and helium gas. Like water flowing down a mountain, the gas was pulled along the invisible filaments, streaming inevitably toward the nodes. As the gas pooled in these deep gravitational valleys, it grew denser and hotter, eventually igniting into the roaring fires of the first stars. For a long time, we thought this process of gathering gas and building galaxies was a slow, agonizingly gradual trickle. But the data from the James Webb Space Telescope suggests something completely different. The presence of the universe-breaking galaxies implies that in the early universe, the flow of gas along the cosmic web was not a gentle stream, but a torrential flood. The dark matter halos were pulling in material at an astonishing rate, force-feeding the young galaxies and triggering explosive eras of star formation. Yet, as scientists analyzed the deep field images, separating the stretched infrared light into its component colors, another impossible realization began to take shape. It was a realization that deepened the silence in the observatories, adding a layer of profound mystery to an already baffling situation. At the centers of many of these massive early galaxies, Webb detected the unmistakable signatures of supermassive black holes. A black hole is a region of space where gravity is so intense that nothing, not even light, can escape its grasp. In our modern, local universe, we know that supermassive black holes sit at the hearts of almost all large galaxies. Our own Milky Way harbors one, known as Sagittarius A star, which is roughly 4 million times more massive than our Sun. These objects are the anchors of their galaxies, holding the swirling masses of stars in a delicate orbital dance. We have always assumed that supermassive black holes, much like the galaxies they inhabit, took billions of years to grow. According to the standard model, a black hole begins its life as a relatively small seed, the collapsed core of a massive dying star. This seed, perhaps a few dozen times the mass of our Sun, then begins a long, slow process of feeding. It pulls in surrounding gas, dust, and the occasional unfortunate star, slowly accumulating mass over eons. There is a fundamental speed limit to how fast a black hole can eat. As gas falls toward the event horizon, the point of no return, it forms a swirling disk. This disk moves incredibly fast, generating immense friction and heat. The material becomes so hot that it blazes with intense radiation, emitting brilliant light and powerful winds. This radiation pushes outward, counteracting the inward pull of the black hole's gravity. When the outward pressure of the light perfectly balances the inward pull of gravity, the black hole reaches what is called the Eddington limit. If it tries to eat any faster, the intense radiation simply blows the food away. Because of this speed limit, it should take a very long time for a stellar mass black hole to grow into a supermassive behemoth. But the James Webb Space Telescope looked back to just a few 100 million years after the Big Bang and found supermassive black holes that were already millions or even billions of times the mass of our Sun. They were fully grown monsters hiding in the dawn of time. The silence that met this discovery was the sound of a physical paradox. If these black holes started as small seeds from the first dying stars, they would have had to consume matter continuously, at their absolute maximum speed limit, for longer than the universe had existed. The math simply did not work. It was as if someone had planted an acorn and, a week later, found a towering, centuries-old oak tree. How could a dark heart grow so large, so quickly, in the quiet infancy of the cosmos? Theories began to surface, spoken in the hushed, careful tones of scientists exploring uncharted territory. One leading idea is the concept of direct collapse. In this scenario, the universe bypassed the small seed stage entirely. In the very early universe, vast, pristine clouds of hydrogen gas, untainted by the heavier elements of later generations, might have collapsed under their own immense weight. Instead of fragmenting to form a cluster of stars, the entire cloud, thousands or tens of thousands of times the mass of the Sun, could have collapsed directly into a massive black hole. These heavy seeds would have provided a massive head start. Born large, they would have a much stronger gravitational pull, allowing them to drag in vast quantities of gas from the surrounding dark matter halo, growing rapidly into the supermassive giants Webb has observed. Another theory suggests that in the chaotic, dense environments of early star clusters, a runaway chain reaction of stellar collisions might have occurred. Massive stars could have merged together, forming a single, unstable giant that quickly collapsed into a heavy black hole seed. As the golden mirrors of the telescope continued to gather the faint stretched light from the edge of the universe, it became clear that the early cosmos was not a quiet, simple place. It was a realm of extremes. It was a place where dark matter built invisible empires, where gas rushed in torrential rivers, and where gravity forged dark, massive hearts at a pace that defies our current understanding of physics. The data is forcing us to confront the reality that our models, as elegant as they are incomplete. The universe has mechanisms of creation and growth that remain hidden in the deep, quiet past, waiting patiently for us to uncover them. There is a limit to how much light even a golden mirror 21 feet across can gather. When observing the very edge of the observable universe, the distances are so vast and the light is so unimaginably faint that human engineering alone is not enough. To look deeper into the silence, the James Webb Space Telescope must rely on a phenomenon that feels less like physics and more like magic. It must use the universe itself as a magnifying glass. In 1915, Albert Einstein published his general theory of relativity, fundamentally changing how we understand gravity. Before Einstein, gravity was thought of as a simple, invisible tether between objects. But Einstein proposed something far more profound. that space and time are inextricably woven together into a single fabric known as space-time. He theorized that massive objects, planets, stars, black holes, and galaxies do not simply sit in space, they rest upon it, bending and warping the fabric of space-time around them. Imagine placing a heavy bowling ball on a stretched rubber sheet. The ball creates a deep depression in the sheet. If you were to roll a marble across the sheet, its path would not be a straight line, it would curve, following the warped surface created by the heavier object. Light, the fastest traveler in the cosmos, must also follow the geometry of space-time. When a particle of light, a photon, travels through the universe, it moves in a straight line. But if that straight line passes near a massive object, the warped space-time causes the path of the light to curve. This gentle bending of starlight is known as gravitational lensing. When the James Webb Space Telescope points its sensors at a massive cluster of galaxies, it is not just looking at the cluster itself, it is looking at a cosmic distortion. A galaxy cluster contains hundreds, sometimes thousands, of individual galaxies, all bound together by the immense invisible mass of dark matter. The combined gravity of this cluster is so staggeringly powerful that it drastically warps the space-time around it. When light from an incredibly distant, incredibly faint galaxy, a galaxy lying far behind the cluster, travels toward Earth, it encounters this warped space. The path of the light is bent, stretched, and magnified, much like the view through the curved glass of a magnifying lens. Without this cosmic assist, the distant galaxy would be entirely invisible, its light too weak to register on our sensors. But through the power of gravitational lensing, the faint light is concentrated and amplified. The warped space-time bends the light path so severely that a single distant galaxy might appear multiple times in the same image. We see smeared, sweeping arcs of light, distorted phantoms of ancient galaxies stretched around the massive foreground cluster. In some rare, perfectly aligned cases, the light from the background galaxy is bent evenly on all sides of the cluster, creating a complete, unbroken ring of light, an Einstein ring. It is a stunning visual confirmation of the theory written over a century ago, a testament to the elegant, interconnected nature of the cosmos. When the first deeply lensed images from Webb were revealed, they were masterpieces of warped light. The sharp, six-pointed stars of the foreground galaxy cluster sat atop a background of swirling, distorted orange and red arcs. It was like looking at the bottom of a clear, rushing stream where the pebbles below are distorted and magnified by the moving water. But scientists were not just captivated by the beauty of the arcs. They were focused on what those arcs represented. By carefully analyzing the warped light, running it through complex computer models that reverse the distortion of the lens, they can reconstruct the true image of the background galaxy. Through this process, the telescope was able to see things that should have been forever lost to the dark. Gravitational lensing allowed Webb to peer inside those early universe-breaking galaxies. It revealed that they are not just undifferentiated blobs of light, but complex structures with distinct, dense regions of star formation. The magnification allowed astronomers to look at the chemistry of the early universe with unprecedented clarity. They aimed their spectrographs, instruments that split light into a rainbow of colors, at these magnified arcs. By studying the specific missing lines in the spectrum, they can determine exactly what elements are present in a galaxy billions of light-years away. In one of the most remarkable silences of the mission, researchers looking through a gravitational lens found the light of a single, individual star. Normally, when we look at distant galaxies, we see the combined, blended light of billions of stars. It is impossible to resolve a single point of starlight across such vast cosmic oceans. But due to a rare, extreme alignment, a specific ripple in the gravitational lens created a localized pocket of immense magnification. The light from this star, given the name Earendel, an Old English word meaning morning star or rising light, was magnified thousands of times. Earendel existed within the first billion years of the universe. It was a massive, brilliant, searing hot star, perhaps 50 to 100 times the mass of our Sun. Seeing Earendel was a moment of profound connection. Across an impassable gulf of time and space, the golden mirror captured the faint, dying whisper of a single star that had burned itself out long before the Earth, or our Sun, or even our Milky Way had ever begun to form. The discovery of Earendel and the detailed chemical mapping of the earliest galaxies through the phenomenon of gravitational lensing shifted the narrative of the early universe once again. The silence in the observatories was no longer just about the shock of massive early galaxies. It was a silence born of intimacy. Through the warped glass of space-time, the universe had allowed us to see its earliest, most fragile moments. We were not just seeing the grand, sweeping structures, we were seeing the individual fires burning in the deep dark. As astronomers continued to map the invisible contours of dark matter and unravel the distorted arcs of ancient starlight, they began to realize that the James Webb Space Telescope was not merely an instrument of observation. It was a time machine, capable of bringing the phantoms of the deep past into sharp, undeniable focus. The story of the universe was being rewritten, not with broad theoretical strokes, but with the precise magnified light of the very first dawn. And there was still so much more to uncover. As we move forward from the sheer, incomprehensible scale of the early universe and the invisible weight of dark matter, we must turn our attention to something that seems entirely ordinary. We must look at dust. On Earth, dust is a nuisance. It is the forgotten debris that settles on old books and empty shelves. But in the grand theatre of the cosmos, dust is the very fabric of creation. It is the ash of dead stars, and it is the cradle of new ones. For generations of astronomers, cosmic dust was a profound frustration. When you look at the night sky with a traditional telescope, or even with the powerful visible light sensors of the Hubble Space Telescope, dust acts as a thick, impenetrable veil. It absorbs visible starlight, casting vast, dark silhouettes across the glowing canvas of the Milky Way. We could see the edges of these dark clouds, but we could not see what was happening inside them. The interiors of these stellar nurseries were locked away in shadow. But the James Webb Space Telescope was not built to look at shadows, because it sees in infrared, which is essentially the faint glow of heat. It can peer directly through the dust. Infrared light waves are longer, allowing them to slip past the microscopic grains of carbon and silicate that block shorter visible light waves. When the telescope turned its golden mirrors toward the Carina Nebula, a massive region of star formation roughly 7,600 light-years away from Earth, the resulting images brought another profound wave of silence over the astronomical community. Before Webb, we had seen this region as a towering, majestic mountain of dark gas, edged by the harsh ultraviolet light of massive young stars. It was beautiful, but it was opaque. When Webb looked at the same region, the mountain of dust seemed to evaporate. The veil was lifted, and for the first time in human history, we could see the deeply hidden engines of creation at work. The scientists looking at these screens did not just see a prettier picture, they saw a dynamic, violent, and astonishingly intricate landscape. They named this region the Cosmic Cliffs. It looks like a craggy coastline under a starry night sky, but that coastline is a wall of gas and dust light years across. It is being carved and eroded by the relentless radiation and stellar winds blowing from immensely hot young stars resting just out of frame. But the true revelation was what lay hidden within the cliffs themselves. Scattered across the landscape were tiny, bright red points of light that had never been seen before. These were protostars. They were infant stars, still in the process of gathering mass, still wrapped in their dusty cocoons. As gravity pulls the gas and dust together, the center grows hotter and hotter. Before nuclear fusion officially ignites, these young objects undergo violent growing pains. They shoot massive, supersonic jets of gas out from their poles, slamming into the surrounding nebula and creating delicate, glowing bow shocks. Through the eye of Webb, we could see these jets tearing through the dark, painting the story of stellar birth in vivid, undeniable detail. The silence that accompanied these images was the silence of witnessing a birth. We were no longer guessing what happened inside the dark clouds of the Milky Way, we were watching it happen. We were seeing the exact, delicate mechanisms that formed our own sun and our own Earth some 4.5 billion years ago. Yet, as Webb peered closer at the dust surrounding these young stars, it found something even more compelling. The dust was not just disorganized debris, it was settling into flat, spinning disks around the protostars. These are protoplanetary disks, the raw material from which planets, moons, asteroids, and comets are forged. This realization naturally guided the telescope's mission toward another profound frontier, the search for other worlds. We live in an era where we know that almost every star in the night sky hosts at least one planet. We call them exoplanets. But finding an exoplanet is only the first step. The next, infinitely more difficult step is figuring out what those planets are actually like. Are they gas giants like Jupiter, swirling with violent storms? Or are they small, rocky worlds wrapped in thin atmospheres, perhaps harboring liquid water on their surfaces? To answer these questions, the James Webb Space Telescope uses a technique called transit spectroscopy. It is a process of incredible precision and quiet elegance. The telescope does not look directly at the planet itself. Even for Webb, a small, rocky planet orbiting a distant star is too faint, entirely lost in the blinding glare of its sun. Instead, the telescope stares unblinkingly at the star and waits. When the planet's orbit carries it directly between the star and the telescope, an event called a transit. A tiny microscopic fraction of the star's light filters through the outer edges of the planet's atmosphere before continuing its journey to Earth. As that starlight passes through the alien air, the gases in the atmosphere absorb very specific wavelengths of infrared light. When the light finally reaches the golden mirrors of the telescope, it is caught and separated into a spectrum, like a rainbow. Scientists then look for missing bands of light in that spectrum. These missing bands are the chemical fingerprints of the atmosphere. When Webb turned its instruments toward an exoplanet called WSP-39b, a hot, puffy gas giant orbiting a star 700 light-years away, the data returned with unprecedented clarity. The spectrum showed undeniable, clear signatures of carbon dioxide. It was the first time in history that carbon dioxide had been definitively detected in the atmosphere of a planet outside our solar system. The scientists reading the graphs in their quiet offices knew exactly what this meant. It was a proof of concept. It proved that the telescope was sensitive enough to read the chemistry of alien skies. It could detect water vapor, it could detect methane, it could detect the very molecules that we associate with life on Earth. The silence that followed this realization was different from the shock of the universe, breaking early galaxies. This was a silence of deep, quiet anticipation. It is the feeling of standing at the edge of an immense ocean, holding a map that is finally coming into focus. We are no longer simply counting planets in the dark. We are beginning to taste their air. We are beginning to chart the chemical makeup of the galaxy. And as the telescope continues to gather the faint infrared whispers of these distant worlds, the possibility that we might one day find an atmosphere out of balance. An atmosphere breathing with the chemical signatures of biological life moves from the realm of science fiction into the quiet, patient reality of observation. When we gather all of these fragments together, the deeply stretched light from the edge of time, the impossibly massive galaxies that defy our timelines, the supermassive black holes born too early, the intricate tapestries of stellar birth hidden in dust, and the chemical signatures of alien skies, we begin to understand the true weight of the James Webb Space Telescope's mission. We begin to understand why the people who built it, and the people who use it, found themselves entirely without words. What James Webb saw made scientists go silent because it dismantled the comfort of certainty. For decades, humanity had painstakingly constructed a model of the universe. We drew a timeline. We set the rules of cosmic evolution. We decided how fast stars could form, how large black holes could grow, and how the intricate dance of dark matter and gas should unfold over billions of years. We thought we had a firm grasp on the narrative of creation. But the universe, in its infinite, quiet wisdom, is under no obligation to follow the scripts we write for it. When the telescope opened its golden eye, it did not reflect our expectations back to us. It held up a mirror to a reality that was vastly more complex, far more efficient, and infinitely wilder than we had ever dared to imagine. The silence in the control rooms was the sound of a paradigm breaking. It was the humbling, profound realization that our mathematical models, no matter how elegant, are just a rough sketch of a masterpiece we are only just beginning to see. This silence is not a defeat. In the pursuit of science, there is no greater joy than being proven wrong by the universe itself. Being wrong means there is still something left to discover. It means the boundary of human knowledge is expanding. The silent awe of the scientist is a testament to the fact that the cosmos is still capable of surprising us, of reminding us that we are a very young species trying to comprehend an ancient, staggering immensity. As we look at the images brought back by this solitary observatory resting a million miles away in the cold, we are forced to re-evaluate our place in the dark. We are made of the very dust at Webb seas swirling around infant stars. The heavy elements in our blood, the calcium in our bones, the iron carrying oxygen to our brains, all of it was forged in the hearts of ancient stars that lived and died in the galaxies we now see as faint, red smudges near the dawn of time. We are not separate from this grand, quiet machinery. We are the universe experiencing itself. Through the polished beryllium and gold of the telescope, we are looking back at our own origins. The silence that fell over the scientific community is the same silence you might feel when you walk outside on a clear, dark night, far away from the lights of the city. When you look up at the band of the Milky Way arching across the sky, there is a natural stillness that comes over you. You do not need a degree in astrophysics to feel the weight of the infinite. You do not need a space telescope to know that the dark above you is full of ancient light and hidden worlds. The James Webb Space Telescope has simply given us a clearer, deeper window into that infinite quiet. It has shown us that the dark is not empty. It is teeming with massive, impossible structures. It is rich with the chemistry of life. It is expanding, shifting, and glowing with the residual heat of its own violent, beautiful birth. Just when we believed the universe had revealed its most profound mysteries through the existence of ancient, massive galaxies and heavy black hole seeds, the James Webb Space Telescope turned its attention to a different kind of problem. This was not a mystery of what the universe is made of, but a fundamental question of how the universe is moving. Since the 1920s, when Edwin Hubble first realized that distant galaxies were rushing away from us, we have known that the universe is expanding. The fabric of space-time is stretching, carrying the galaxies along with it. For nearly a century, one of the primary goals of cosmology has been to measure the exact speed of this expansion. We call this speed the Hubble constant. Finding the exact value of the Hubble constant is not just an exercise in bookkeeping, it is the key to understanding the age, the evolution, and the ultimate fate of the entire cosmos. If you know how fast the universe is expanding today, you can run the clock backward to find out exactly when the Big Bang happened. You can also run the clock forward to see if the universe will expand forever, tearing itself apart in a cold freeze, or if it will eventually collapse back in on itself. To measure this expansion, astronomers use two completely different methods. The first method looks at the very beginning of time. By studying the cosmic microwave background, the faint, lingering radiation left over from the Big Bang itself, scientists can measure the exact conditions of the early universe. Using our standard model of cosmology, they take those early conditions and calculate how fast the universe should be expanding today. The second method looks at the local, modern universe. Astronomers use telescopes to look at specific types of pulsing stars called Cepheid variables, and specific types of exploding stars called Type Ia supernovae. These objects act as cosmic milestones or standard candles. Because we know exactly how bright they truly are, we can measure how dim they appear to figure out exactly how far away they are. By combining their distance with how fast they are moving away from us, we can measure the current expansion rate directly. For years, these two methods have yielded two different numbers. The The measurements from the early universe predicted a slower expansion rate. The measurements from the modern universe showed a faster expansion rate. This discrepancy became known as the Hubble tension. At first, scientists were not entirely silent about this. There was a lot of healthy debate. Many astronomers believed that the tension was simply a measurement error. They assumed that our view of the modern universe, captured primarily by the Hubble Space Telescope, was somehow flawed. Perhaps dust was interfering with the light of the standard candles. Perhaps the calibration of the instruments was slightly off. They eagerly awaited the launch of the James Webb Space Telescope, confident that its incredibly sharp infrared eye would correct the errors, align the numbers, and save the standard model of cosmology. Webb was tasked with looking at the very same Cepheid variable stars that Hubble had measured, but with far greater precision. Because Webb sees in infrared, it can pierce right through the interstellar dust that might have been confusing Hubble's visible light sensors. When the data from Webb was finally processed, the quiet that descended upon the astronomical community was heavy with implication. Webb did not find an error in Hubble's measurements. In fact, Webb confirmed them perfectly. The data was immaculate. The standard candles were exactly where we thought they were, and they were moving exactly as fast as we had measured. The silence was the realization that the Hubble tension is not a mistake. It is real. The universe is genuinely expanding faster today than the laws of physics say it should be. This means that our understanding of the cosmos is not just incomplete, it might be fundamentally broken. There is something missing in our standard model. Perhaps there is a new, undiscovered type of particle. Perhaps dark energy. The mysterious force driving the acceleration of the universe is not constant, but changes over time in ways we do not yet understand. Or perhaps the very laws of gravity behave differently on a cosmic scale than they do on a local scale. The pristine data from the James Webb Space Telescope stripped away our excuses. It forced cosmologists to look at the blank spaces on their chalkboards and admit that a major piece of the universe's machinery remains entirely hidden from us. We are living in a fractured timeline, trying to stitch together a story of expansion that simply refuses to hold its shape. While cosmologists grappled with the fractured expansion of the universe, another team of scientists pointed the James Webb Space Telescope much closer to home. They looked away from the edge of time and focused on a bright, churning cloud of gas in our own Milky Way, the Orion Nebula. Located just over 1,000 light-years away, the Orion Nebula is one of the closest and most active stellar nurseries to Earth. It is a chaotic, beautiful environment where massive, brilliant stars illuminate the surrounding gas, carving vast caverns of dust with their intense radiation. Astronomers aimed Webb's near-infrared camera at the heart of the nebula, a region known as the trapezium cluster. They were looking to study the delicate protoplanetary disks of gas and dust that swirl around young stars. They wanted to understand the fine details of how planets are born. But as they scanned the deep, high-resolution infrared images, they found something drifting in the dark spaces between the stars. They found objects that should not exist. They discovered roughly 40 pairs of massive, Jupiter-sized objects floating freely through the nebula. They are not orbiting any star. They are simply wandering through the cold dark, bound only to each other. The scientists named them JUMBOs, Jupiter mass. Binary objects. To understand why the discovery of JUMBOs caused theorists to fall silent, we have to look at how we believe planets form. In the standard model of planetary formation, planets are born within the dusty disk surrounding a new star. A star forms first, gathering the vast majority of the mass. The leftover material flattens into a spinning disk. Inside that disk, dust grains stick together, growing into pebbles, then boulders, then rocky cores. If a core grows large enough, it can sweep up massive amounts of hydrogen and helium gas, becoming a gas giant like Jupiter. According to our models, you cannot form a Jupiter without a star. A gas cloud floating alone in space simply does not have enough mass to collapse and ignite into a star, and it shouldn't be able to compress itself tightly enough to form a planet-sized object on its own. There is, of course, the phenomenon of rogue planets. We know that young solar systems are violent, chaotic places. As planets form and migrate, their gravitational fields interact. Sometimes, a planet can be violently ejected from its solar system, cast out into the interstellar void to wander alone forever. But the jumbos in the Orion Nebula are not single rogue planets. They are in pairs. Imagine the sheer mechanical improbability of a young solar system violently ejecting two Jupiter-sized planets at the exact same time, in the exact same direction, with the exact same velocity, so that they remain gravitationally bound to each other as they fly out into the dark. It is like trying to violently shatter a pane of glass and expecting two specific shards to perfectly fuse together in mid-air. The physics of ejection simply do not support the existence of binary rogue planets in such high numbers. Yet there they are, glowing faintly with the residual heat of their own formation, captured in undeniable detail by Webb's infrared sensors. The silence that met the discovery of the jumbos was the silence of theorists realizing their models of planetary formation were too rigid. We thought we understood the strict boundary between stars and planets. Stars form from collapsing clouds, planets form in disks. The jumbos blur that line entirely. Perhaps they form directly from the collapse of tiny, impossibly dense pockets of gas in the nebula, bypassing the need for a host star entirely. If so, it means the universe is capable of manufacturing giant planets through mechanisms we have never even theorized. As we look at the wanderers in the dark of the Orion Nebula, we are reminded once again of the recurring theme of the James Webb Space Telescope's mission. Whether it is looking billions of light years away at the dawn of time or peering into our own local galactic neighborhood, the telescope consistently reveals a cosmos that is infinitely more creative than our textbooks. We build models to make sense of the vastness. We draw lines and set rules to give ourselves a sense of order in the dark. But the universe is not bound by our desire for order. It is a wild, dynamic, and breathtakingly complex place. The golden mirrors of the James Webb Space Telescope have not given us all the answers. Instead, they have given us something far more valuable. They have given us a better, deeper, and more profound set of questions. As we continue to float on our small rocky world, listening to the quiet of the cosmos, we know that the dark still holds countless secrets. And we will keep looking, keep wondering, and keep listening to the silence, waiting for the universe to surprise us once again. Thank you for joining me on this long, meditative journey through the edge of space and time. I hope this exploration has given you a moment of peace and a new way to think about the vast, silent universe we call home. Keep looking up at the night sky, keep wondering about the dark, and until next time, take care. Time is a river. It flows around us, often unnoticed, measured in the ticking of clocks, the beating of hearts, and the rising of the sun. But in the vast velvet silence of the cosmos, time is measured differently. It is measured in the slow rotation of galaxies, the birth of stars, and the silent drifting journeys of ancient stone, 1 minute ago. 60 seconds. In the time it took for you to take a few breaths, a signal crossed the void. It traveled through the emptiness of space, moving at the speed of light, carrying a message from the dark. It arrived quietly. There were no sirens. There was no panic. There was only the silent hum of a server in a cool, dimly lit room and a line of data appearing on a screen. 1 minute ago, NASA detected something approaching Earth. But to understand this moment, this single fleeting minute, we must slow down. We must step away from the noise of our daily lives, from the rush of traffic and the glow of our phones. We must transport our minds to a place of absolute stillness. Imagine the Mojave Desert. It is night. The air is cool and thin, carrying the scent of dry sagebrush and ancient dust. Above, the sky is a sprawling canvas of diamonds, the Milky Way stretching like a bridge of light across the darkness. Here, standing tall against the horizon, is a massive white dish. This is the Goldstone Deep Space Communications Complex. It is a giant ear listening to the whispers of the universe. The dish is 70 meters wide, a marvel of engineering, yet it stands perfectly still, angled toward a specific point in the sky. It is waiting. It is always waiting. It listens to the faint radio waves emitted by spacecraft billions of miles away. It listens to the echoes of radar bouncing off passing asteroids. 1 minute ago, this dish caught a whisper. The object it detected is not a stranger, it is a neighbor. It is a traveler that has been wandering the solar system for billions of years, long before the first life emerged on Earth, long before the oceans filled, long before the atmosphere settled into the blue blanket we know today. This traveler is a small asteroid, a piece of the primordial puzzle. It is roughly the size of a house, a tumbling, silent shape made of rock and metal, forged in the fires of the early solar nebula. It is dark, reflecting only a tiny fraction of the sunlight that touches it, which is why we are only seeing it now as it draws near. Approaching Earth can sound alarming. It summons images of collision, of fire and impact. But in the language of astronomy, approaching is a gentle term. It means passing by. It means a visit. Think of two ships passing in the middle of a vast, calm ocean in the dead of night. They may be miles apart, unseen to the naked eye, known to each other only by the blips on a radar screen. They approach, they pass, and they drift apart again into the mist. This is what is happening right now, high above your head. The object, let us call it the traveler, is gliding through the vacuum. It is cold, colder than the deepest winter on Earth. Its surface is pockmarked with tiny craters, the scars of 1 billion years of silent collisions with dust and sand. It spins slowly, tumbling end over end, dancing to the silent rhythm of gravity. 1 minute ago, the light reflecting off this tumbling stone reached the sensors of our telescopes. The data flowed down through the atmosphere, invisible and silent. It was caught by the curved mirrors and the radio dishes. It was turned into numbers, coordinates, speed, trajectory. The computers calculated the path. They drew a line through the darkness of the future, and the result was a reassurance. The traveler will pass us safely. It will miss our blue marble by millions of miles, a hair's breadth in cosmic terms, but a vast, safe ocean in human terms. There is something profound about this detection. It reminds us that we are not isolated. We are not sitting in a sealed room. We are living in a busy, active system. The solar system is not empty space. It is a crowded harbor. There are currents of dust, rivers of radiation, and fleets of rocks and ice, all moving in a grand, complex choreography. When NASA detects something approaching, it is like a lighthouse keeper spotting a distant sail on the horizon. It is an acknowledgement of presence. I see you, the telescope says. I see you, traveler from the dark. Let us drift out to meet it. Close your eyes and imagine leaving the surface of the Earth. Rise up through the clouds, past the realm of airplanes and birds. Rise until the sky turns from blue to indigo and from indigo to black. You are floating in the silence of low Earth orbit. Below you, the world is a glowing gem, blue and white, spinning slowly. You can see the lights of cities, glowing like embers in a fireplace. You can see the thin, fragile line of the atmosphere, the only shield protecting all of life from the void. Turn away from the Earth now. Look out into the black. Somewhere out there, in the deep shadow, the traveler is moving. It is moving at thousands of miles per hour, yet if you were drifting beside it, it would seem to be hanging motionless. Speed is relative in the void. Without wind to rush past your ears, without trees to blur in your vision, speed becomes a silent mathematical fact rather than a physical sensation. It is peaceful here. There is no sound, no vibration, just the endless starlight and the silent motion of celestial bodies. The traveler has come from the asteroid belt, a vast ring of debris drifting between Mars and Jupiter. Perhaps millions of years ago, it was nudged by the gravity of Jupiter, that giant, benevolent shepherd of the solar system. That nudge changed its path. It sent the stone on a long, elliptical journey inward toward the Sun. It has crossed the orbit of Mars. It has felt the warmth of the Sun growing stronger on its rocky skin. It has seen the Earth as a pale blue dot, growing brighter and larger with each passing decade. And now, 1 minute ago, it has arrived in our neighborhood. This detection is a triumph of stillness. To see something so small, so dark, and so fast requires patience. It requires the ability to stare at the same patch of sky for hours, waiting for a single pixel to move. The astronomers who watch the sky are the sentinels of humanity. But they are not soldiers watching for enemies, they are naturalists watching for wildlife. They are cataloguing the ecosystem of our star system. Every rock they find, every path they map, adds a page to the great book of our history. So, when the notification flashes, asteroid detected, it is not a warning siren, it is a bell of mindfulness. It rings to tell us, look up, look out, there is movement in the dark, we are safe. The atmosphere protects us from the small dust. The vast distances protect us from the large stones. We are cradled in a gravitational sweet spot, protected by the massive bulk of Jupiter and the Moon, spinning in a stable orbit. But for this moment, let us honor the passing of this silent stone. It is a relic of creation. It contains the same atoms that make up the core of our planet. It is a distant cousin, visiting from the cold lands, passing by to warm itself by the fire of our sun before drifting back out into the night. 1 minute ago we saw it, and in seeing it we connected, briefly, with the deep, slow pulse of the universe. As the traveler passes, let us widen our gaze. Let us step back from the single object and look at the medium through which it moves. We often call it space, a word that implies emptiness. We call it a vacuum, implying a void. But to the cosmos, this is not empty. It is an ocean, a vast, dark, silent ocean of night. Just as the oceans on Earth are teeming with currents, drifts, and unseen forces, the space around our planet is alive with invisible energy and matter. When NASA detects an object approaching Earth, they are tracking a vessel moving through this ocean. But what is the water? What is the substance of the void? It is gravity. Gravity is the current of the cosmos. It is the invisible river that guides every star, every planet, and every speck of dust. It is a gentle, relentless force. It does not shout, it pulls. It curves the fabric of space itself, creating slopes and valleys that objects naturally follow. The traveler, that small asteroid we detected moments ago, is not using an engine. It is not burning fuel. It is simply falling. It is falling along the curve of gravity created by the sun. It is surfing the largest wave in the solar system, a wave that takes years to crest. Imagine yourself floating in this gravitational ocean. You are weightless. The heavy chains of Earth's pull have loosened. You are free. Around you, the darkness is not flat. It has depth. It has texture. Every object with mass creates a dimple in this fabric. The Earth creates a deep well, a cozy pocket of gravity that holds the Moon on its leash. The Sun creates a massive, sweeping valley that holds all the planets in their orbits. Our approaching visitor is sliding along the edge of Earth's gravity well. It feels the pull of our planet, a gentle tug, like a hand reaching out to graze a shoulder. This tug might alter its path slightly, a gravity assist. The Earth will whisper to the asteroid, changing its trajectory by a fraction of a degree, sending it off onto a new course, perhaps to return in another 100 years, perhaps never to be seen again. This dance happens in total silence. Let us look closer at the space immediately surrounding Earth. We call this near-Earth space. It is a busy region. It is not just the domain of satellites and space stations. It is a dusty place. Every day, Earth is approached not just by large rocks, but by tons of cosmic dust. Micrometeoroids, tiny grains of sand left over from the tails of comets that passed by centuries ago. NASA detects the big things, the ones that matter for planetary safety. But who detects the dust? Who sees the tiny sparkles that approach Earth every second? You do. If you have ever stood in a dark field and looked up to see a shooting star, you have detected something approaching Earth. That streak of light, that fleeting scratch on the chalkboard of the night, is a grain of cosmic sand hitting the atmosphere at 40,000 miles per hour. It is a violent event, transformed by distance and atmosphere into a moment of pure beauty. The air molecules glow with the heat of the friction, creating a tube of plasma that we see as a shooting star. It is a reminder that the barrier between us and space is soft. The atmosphere is a membrane, permeable to light and heat, but a shield against the stone. As we contemplate the object detected 1 minute ago, we realize that approaching is a relative term. In the scale of the universe, everything is far away. The moon is 250,000 miles away. The sun is 93 million miles away. When an object comes within a few million miles of Earth, astronomers call it a close approach. But this distance is still vast beyond human comprehension. If you could drive a car towards this object at highway speeds, it would take you years to reach it. The fear that often accompanies headlines, "Asteroid approaching," comes from a misunderstanding of scale. The universe is mostly space. The chances of collision are infinitesimally small. It is like 2 grains of sand thrown into the Grand Canyon. The odds of them hitting each other in mid-air are nearly zero. So we can let go of the fear. We can replace it with awe. We can appreciate the precision. The mathematics required to detect these objects is staggering. It is like standing in New York and spotting a specific mosquito flying in Tokyo. Yet, our scientists and engineers do this every day. The Deep Space Network, with its dishes in California, Spain, and Australia, ensures that we are never blind. As the Earth rotates, one dish hands off the duty to the next, passing the baton of observation so that the sky is never unwatched. There is a rhythm to this surveillance, a slow, steady scanning. The telescopes take images of the sky, night after night. Computers overlay these images, looking for the dot that moves against the background of fixed stars. Stars do not move relative to one another over the course of a night. They rise and set together, a fixed tapestry. But the wanderers, the planets, the comets, the asteroids, they possess their own motion. They are the restless ones. When the computer spots a moving dot, it flags it. Here, it says, here is something new. 1 minute ago, that flag was raised. A human being, perhaps sipping coffee in a quiet control room, looked at the data. They checked the orbit. They verified the path. They saw that it was safe. And then they catalogued it. They gave it a name, likely a string of numbers and letters. 2024. BX1. A license plate for a cosmic vehicle. This act of naming is an act of caring. By tracking these stones, we are extending our awareness outward. We are mapping our backyard. We are becoming responsible citizens of the solar system. Let us return to the object itself. Imagine you are drifting right next to it now. The sun is a blazing star in the distance, smaller than it looks from Earth, but fiercely bright in the unfiltered vacuum. The sunlight strikes the side of the asteroid, illuminating the grey, dusty surface. It is ancient. This rock has not changed in 4.5 billion years. On Earth, wind and rain and life constantly reshape the surface. Mountains wear down, rivers change course, cities rise and fall. But here, on this lonely traveler, time stands still. The crater on its side was made by a collision 1 billion years ago. The dust clinging to its ridges has been there since the time of the dinosaurs. It is a museum piece, a pristine sample of the dawn of time. If you could touch it, though your hand would freeze instantly, you would be touching the raw material of creation. This is the stuff that Earth was made of. We are standing on a giant collection of asteroids that fused together billions of years ago. We are, in a sense, made of the same material as the visitor passing us by. We are kin. Earth is simply the asteroid that grew up. The asteroid that gathered enough mass to hold an atmosphere, to distill water, to birth life. The traveler is our silent, sleeping brother who never woke up, who never grew warm, who stayed out in the cold, preserving the memory of our shared beginning. So, as it approaches, do not see a threat. See a family member. See a memory. The darkness around it is not empty. It is filled with the solar wind, a stream of charged particles flowing out from the sun. This wind washes over the asteroid, stripping away tiny atoms, weathering it imperceptibly slowly. It is also filled with light. The light of distant stars, the light of the Milky Way, the faint glow of the zodiacal light, dust reflecting the sun in the plane of the solar system. The traveler moves through this cathedral of light and shadow with total indifference. It has no destination. It has no schedule. It only has a path, dictated by the curvature of space, defined by the mass of the sun. It reminds us of the virtual drifting. In our lives, we are obsessed with destinations. We must be somewhere. We must achieve something. We rush from point A to point B, anxious about being late. But the universe does not rush. The universe drifts. The galaxies drift through the intergalactic void. The stars drift around the galactic core. The planets drift in their ellipses. This object, detected 1 minute ago, is a master of drifting. It surrenders completely to the forces around it. It does not fight gravity, it accepts it. It allows the universe to carry it. Perhaps we can learn from this. Perhaps, in this hour of contemplation, we can allow ourselves to drift. We can release the tension in our shoulders. We can unclench our jaws. We can stop steering the ship of our lives for just a moment and let the current take us. We are, after all, on a spaceship. Earth is a ship. We are all passengers on a massive sphere of rock and iron, drifting around a star which is drifting through a galaxy which is drifting through the universe. We are already floating. We are already flying. The detection of the asteroid is just a momentary glance out the window of our spaceship, seeing another vessel passing in the night, reminding us of where we are. We are in the deep. We are in the calm. We are in the embrace of the cosmos. To understand the visitor that passed us 1 minute ago, we must unwind the clock. We must not just go back minutes or days. We must go back before the existence of days. We must return to the time before the Earth had a shape, before the sun had ignited, to the very womb of our celestial history. 4.5 billion years ago. The space where you are sitting now was not empty, but it was not organized. It was a vast, swirling cloud of gas and dust, a nebula, a nursery of stars. It was cold, dark and silent, stretching for light years in every direction. In this cloud, there were grains of diamond, specks of graphite and crystals of ice. These were the seeds of worlds. Gravity, the great sculptor, began its work. It pulled the dust together. Grain by grain, pebble by pebble, the cloud began to collapse. In the center, the pressure grew immense. The heat rose. And suddenly, light. Our sun was born, a fusion engine igniting in the dark, blasting a wind of energy outward. This wind pushed the lighter gases away, leaving the heavy rocks and metals to drift in the inner warmth. This is the era of chaos, a time of violent beauty. Millions of rocks swirled around the infant sun, colliding, merging, shattering. They were like dancers learning their steps, stepping on toes, stumbling, until they found their rhythm. The object that NASA detected 1 minute ago was born in this moment. It is a survivor. While its siblings collided to form the Earth, Mars, and Venus, this particular stone escaped. It was not consumed by a growing planet. It was not cast out into the frozen dark of the outer void. It found a quiet pocket of space. It found a hiding place in the asteroid belt. For eons, it drifted there. It witnessed the solar system settling down. It saw the planets sweep their orbits clean, becoming the masters of their lanes. It saw the bombardment of Earth, the rain of comets that brought our oceans, the impacts that tilted our planet to give us seasons. It watched from a distance. It was a silent witness to our entire history. When single-celled life first stirred in the primordial soup of Earth, this rock was floating millions of miles away, turning slowly in the dark. When the first fish crawled onto land, it was there. When the dinosaurs rose to dominance and when they vanished, it was there. When the ice ages came and went, painting the Earth in white and green, it kept its lonely watch. And now, after 4 billion years of solitude, gravity has invited it for a visit. This context changes how we feel about the detection. It is not a random rock thrown at us, it is a time capsule. If we could crack it open, we would find the pristine chemistry of the early solar system. We would find water molecules that have been frozen since the beginning of time. We would find organic compounds, the carbon-based building blocks of life. In a way, this approaching object carries the recipe for us. NASA's detection is not just about planetary defense, it is about archaeology. We are digging in the sky. Every time we spot one of these near-Earth objects, we are cataloging an artifact from the Museum of Creation. The fact that we can see it is a miracle of light. This object produces no light of its own. It is dead stone. But the Sun, our shared parent, bathes it in photons. The light hits the grey, cratered surface and bounces off. It travels millions of miles, spreading out, growing fainter and fainter, until a tiny fraction of it enters the aperture of a telescope. That light is old. It took minutes to travel from the rock to us. We are always seeing the past. When we look at the moon, we see it as it was 1 second ago. When we look at the sun, we see it as it was 8 minutes ago. And when we look at this asteroid, we are seeing a ghost of its position. The universe is a hall of mirrors reflecting images across time. As this ancient stone passes Earth, it enters a region teeming with a different kind of evolution. It passes through the sphere of human influence. It passes the geostationary satellites, hanging like jewels in a fixed ring above the equator. It passes the GPS constellations, the weather watchers, the internet beamers. It passes the debris of our own making, spent rocket stages, bolts, paint chips, our own artificial asteroid belt that we are creating. There is a stark contrast here. The natural asteroid is billions of years old, shaped by the slow, grinding forces of nature. The artificial satellites are decades old, shaped by the rapid, frantic ingenuity of humans. The meeting of these two worlds, the ancient rock and the modern machine, is the story of our time. We are the children of the solar system reaching out to touch the parents. We are the dust that woke up, built eyes of glass and metal, and looked back at the dust that remained asleep. This perspective brings a sense of tenderness. We are not fighting the universe, we are trying to understand it. We are trying to map the family tree of the solar system. When the alert comes, 1 minute ago, something was detected. It is a notification that a family member has walked into the room. We turn our heads, we acknowledge them, and we let them pass, continuing their eternal journey around the fire of the sun. The fear of the cosmos often stems from a feeling of vulnerability. We stand on the surface of our world looking up at the open sky, and we feel exposed. There is no roof over our heads. There is only air thinning out into nothingness. But this feeling is an illusion. We are not exposed. We are armored. We are protected by invisible shields of immense power, forces that have guarded life on Earth for billions of years. The first shield is one we rarely think about: the gas giants. Far beyond the orbit of Mars, in the cold outer reaches, reigns the king of planets, Jupiter. It is a colossus, a ball of gas so massive that it could hold 1,300 Earths inside it. Its gravity is a deep, powerful well. Jupiter acts as the gatekeeper of the inner solar system. For billions of years, its gravity has been catching comets and asteroids that fall inward from the dark edges. It swallows them. It flings them out of the solar system entirely. It herds them into stable orbits where they cannot harm us. Without Jupiter, the Earth would be a shooting gallery. But the king stands watch. It takes the blows so we don't have to. The scars of 1,000 impacts are hidden in its swirling cloud storms the size of continents that have raged for centuries. The object that approached us 1 minute ago likely survived because it stayed out of Jupiter's way. Or perhaps it was Jupiter that nudged it onto this safe path, threading the needle between the planets. The second shield is closer to home, the Moon. Our silent silver companion is not just a nightlight, it is a shield bearer. Look at the face of the Moon through binoculars. It is pitted, cratered, scarred. Every one of those pockmarks represents a collision that did not happen to Earth. The Moon has been taking hits for us since the beginning. It orbits us like a guard dog, sweeping its path clear. But the most intimate shield, the one that hugs us tightest, is the atmosphere. We think of air as soft. We move through it easily, we breathe it. But at high speeds, air becomes harder than concrete. When an object from space approaches Earth, it hits the upper atmosphere at tremendous velocity, anywhere from 25,000 to 160,000 miles per hour. At that speed, the air cannot move out of the way fast enough. It compresses. And compression creates heat. Intense, blinding heat. Most of the threats detected by NASA are small. They are the size of beach balls or cars. When they hit our invisible shield, they do not stand a chance. They disintegrate. They turn into streaks of light, vaporizing into harmless dust that slowly drifts down to settle on our rooftops and in our oceans. The Earth is constantly dusting itself with the remnants of these visitors. The object detected 1 minute ago, the one the size of a house, is large enough that it could survive the atmosphere if it were on a collision course. But even then, the atmosphere would fight it. It would break it apart, it would slow it down, it would absorb the energy. But it is not on a collision course. And this brings us to the final, most mathematical shield, probability. Space is big. It is incomprehensibly, staggeringly big. Imagine the Earth as a single grain of sand floating in the middle of a football stadium. Now, imagine another grain of sand, the asteroid thrown randomly into that stadium. The chances of those two grains touching are vanishingly small. The headlines focus on the close approaches. They tell us when a rock comes within 4 million miles. But 4 million miles is a vast distance. It is 16 times the distance to the Moon. NASA's planetary defense systems are not designed to panic us. They are designed to give us the gift of time. If, and it is a big if, we ever detected an object on a true collision course, we would likely know years, perhaps decades in advance. We would not be looking up at a fireball in the sky tomorrow. We would be looking at a dot on a screen, a problem to be solved by the next generation, and we would solve it. We have the technology now to nudge a rock. We have tested it. We have reached out and touched an asteroid, altering its path just enough to turn a hit into a miss. We are the first species in the history of this planet that can protect itself from the stars. The dinosaurs could only look up and wonder. We can look up, calculate, and act. So, the detection from 1 minute ago is a testament to our competence. It is a signal that the watchmen are awake. The radar dishes are spinning, the telescopes are open, we can sleep soundly. As the asteroid fades into the distance, moving away from Earth and back into the deep dark, it leaves us behind. It leaves us in our bubble of blue, protected by giants, shielded by air, and watched over by human ingenuity. The silence returns to the control room. The data stream slows. The object becomes just another entry in the database, another number in the catalogue of the heavens. But the feeling remains, the feeling of connection, the feeling of scale. We are small, yes, but we are aware. And in a universe of blind, tumbling stone, awareness is the most precious thing of all. We have spoken of the object, the traveller of stone. We have spoken of the shield, the armour of the earth. Now, let us speak of the mind that watches. 1 minute ago, a machine detected a signal. But behind that machine was a human intention. For thousands of years, our ancestors looked at the night sky with a mixture of awe and fear. They saw comets as bad omens, swords of fire hanging over kings. They saw eclipses as dragons eating the sun. They felt small, at the mercy of capricious gods who lived in the stars. But today, we have changed the relationship. We no longer look up with fear. We look up with curiosity. We look up with understanding. The detection of this asteroid is a symbol of our maturity as a species. We have moved from being passive observers to active guardians. We have built a network of eyes, optical telescopes on mountain peaks in Hawaii and Chile, radio telescopes in valleys, infrared telescopes floating in the cold vacuum of space. These are the watchers on the wall. They never sleep. When the sun rises in Arizona, the telescopes in the Canary Islands are opening their domes. When the clouds cover the sky in Europe, the radar in Australia is pinging the void. There is a profound comfort in knowing this. While you sleep, while you dream, there are sentinels awake. They are scanning the darkness, measuring the orbits, ensuring that the path ahead is clear. This global effort is one of the few things that truly unites us. The asteroid does not care about borders. It does not care about nations or politics. If it were to touch the atmosphere, it would touch the Earth as a whole. And so, our defense is whole. Data shared between continents, science shared between languages. In the face of the cosmic scale, our differences vanish. We become simply the people of Earth. Let us return to the moment of detection. 1 minute ago. That moment passed without you noticing. You were perhaps drinking water, or turning a page, or closing your eyes, and yet, in that silence, a victory occurred. The victory of knowledge. We know where we are. We are not lost in the dark. We have a map. Think of the early sailors navigating the vast oceans of Earth. They relied on the stars to find their way, but they did not know what the stars were. They sailed into the fog, hoping to avoid the rocks. We are sailing the ocean of space, but we have radar. We have sonar. We have charted the shoals and the reefs. We know where the icebergs drift. This asteroid, this silent visitor, is just a passing ship that we have hailed. Safe journey, we say. Pass in peace. And it does. It continues on its way, moving toward the orbit of Venus, perhaps. It will warm up, releasing a faint tail of gas, before swinging back out toward the cold. It will be lonely again for another century. But for a brief moment, it was seen. It was known. There is a philosophy here, a cosmic stoicism. We accept that we live in a dynamic, moving universe. We accept that there are rocks flying through the dark. We do not deny the danger, but we do not live in fear of it. We prepare, we watch, and then we live. The awareness of the asteroid makes the blue sky look sweeter. It makes the air feel fresher in our lungs. It makes the stability of the ground beneath our feet feel like a gift, not a guarantee. We are riding on a rock that has been safe for millions of years. Life has continued unbroken through ice and fire, through impact and eruption. The chain of life is strong. You are the latest link in that chain. The asteroid passing by is a reminder of your resilience. You are here because your ancestors survived. You are here because the Earth is tough. You are here because the shields held. So, let this knowledge settle into your bones. Let it be a weight that grounds you, rather than a worry that lifts you. You are part of a protected system. You are part of a watchful species. You are safe. And now, the minute has passed. The hour has passed. The Earth has rotated further on its axis. The stars that were in the east are now high overhead. The object is gone. It has crossed the invisible line of closest approach and is now receding. The distance between us and the stone is growing. Every second, it adds miles to the gap. It is fading into the black, becoming smaller, dimmer, quieter. The telescopes have done their job. The computers have logged the data. The alert status returns to green. The quiet hum of the servers continues, ready for the next visitor, the next wanderer. Let us bring our awareness back from the edge of space. Bring your mind back down through the layers of the atmosphere, down through the ionosphere, where the aurora dances in curtains of green and violet. Down through the stratosphere, where the air is thin and cold. Drift down through the clouds. See them from above, like a vast field of white cotton, illuminated by the moon or the sun. Descend further until you see the lights of your home. You see the streets, the trees, the roof of the building where you rest. You are back. You are here. The vastness of space is still there, just above your head, but it feels different now. It is not a void of terror. It is a blanket of stars that wraps around the world, holding us in. The detection that happened 1 minute ago is now part of history. It is one of billions of events that happen every day in the clockwork of the solar system. The sun will rise tomorrow, just as it has for 4 billion years. The gravity of the Earth will hold you securely to your bed. The atmosphere will breathe for you. You can let go of the vigilance. You do not need to watch the sky. The machines are doing it for you. The scientists are doing it for you. You have permission to rest. As the asteroid drifts away, let your thoughts drift with it. Let them float away into the deep silence. Imagine your worries are like that stone, tumbling, turning, but moving away from you. They are becoming smaller. They are disappearing into the dark. You remain. You remain in the light. You remain in the warmth. The universe is vast and old and mysterious, but it is also orderly. It follows rules. It dances to a rhythm, and you are part of that rhythm. Your heart beats in time with the rotation of the planet. Your breath flows in time with the tides. We are living inside a cosmic void, yes, but we are also living inside a sanctuary, a blue oasis in the desert of night. 1 minute ago, NASA detected something, and now, silence, peace, stillness. The screen is dark, the sky is clear, the traveler has passed. We have watched the visitor arrive, and we have watched it depart. But the story does not end with the passing of a single stone. The story continues into the deep future, into the era where observation becomes stewardship. Let us cast our minds forward. Not 1 minute ago, but 1,000 years from now. Imagine the Earth then. It is still blue, still turning, still wrapped in its blanket of clouds. But the silence above it has changed. The watchers on the wall are no longer just telescopes on mountains. They are out there, among the stones. In this quiet future, humanity has accepted its role. We are no longer just survivors hiding on a planet. We have become the gardeners of the void. The solar system is a wild place, filled with the debris of creation. For billions of years it was a chaotic wilderness where rocks tumbled blindly in the dark. But slowly, gently, we are taming it. We are mapping the wilderness. In this future, every asteroid, every comet, every drifting grain of sand has a name. They are not threats, they are catalogued members of the system. We know their paths as well as we know the currents of our own oceans. And when a stone approaches Earth in that distant time, we do not just watch, we reach out. Imagine a vessel, silent and sleek, moving through the vacuum. It does not carry weapons, it carries gravity. It glides alongside a drifting asteroid, matching its speed, hovering like a hummingbird beside a flower. It does not touch the rock. It simply uses its own mass, a gentle gravitational tug, to whisper to the stone. Move this way, it suggests, just a little to the left. Over months and years, that tiny whisper changes the path of the mountain. The asteroid drifts safely past Earth, guided by the hand of the gardener. This is the future of planetary defense, not explosions, not drama, but a gentle, silent dance of physics, a cosmic ballet where we lead the stones into safe harbors. This vision brings a deep sense of peace. It suggests that chaos is not the final state of the universe. Intelligence brings order. Consciousness brings safety. Just as we learned to build levees to guide the rivers, just as we learned to build roofs to shelter from the rain, we are learning to guide the rivers of gravity and shelter from the rain of stars. We are growing up. The detection that happened 1 minute ago in our present time is the first step of a toddler learning to walk. We are just beginning to open our eyes. We are just beginning to understand the layout of the room. But the potential is there. Written in our DNA is the urge to protect, the urge to nurture. We are extending that urge outward, past the atmosphere, past the moon, into the black. Think of the asteroid belt not as a field of danger, but as a future resource. Those drifting stones are made of iron, nickel, platinum, and water. They are the building blocks of the future. One day, perhaps the descendants of that stone we detected will not pass us by. Perhaps they will be caught gently and used to build new habitats, new stations, new homes in the void. The threat becomes a gift. The danger becomes a tool. This is the alchemy of time. What we fear today, we master tomorrow. What we watch with anxiety today, we will hold with gratitude tomorrow. So, when you hear of an object approaching Earth, do not shrink back. Stand tall. Feel the long thread of history stretching out from you into the future. You are the ancestor of the gardeners. You are the one who started watching. The silence of space is not an empty silence. It is a waiting silence. It is waiting for us to fill it with meaning, with names, and with care. Let us take one final step back. Let us leave the solar system entirely. We have spoken of minutes. We have spoken of years. We have spoken of millennia. But there is a clock that ticks much slower than any of these. The galactic clock. Our sun is not stationary. Just as the Earth orbits the sun orbits the center of the Milky Way galaxy. It is a journey of incomprehensible scale. We are moving at 500,000 miles per hour, dragging the Earth, the planets, and all the asteroids with us. We are a caravan of light moving through the dark forest of the galaxy. It takes the sun 230 million years to complete one orbit. One galactic year. The last time we were in this part of the galaxy, dinosaurs were just beginning to appear on Earth. The time before that, life had not yet crawled onto land. The asteroid that we detected 1 minute ago is traveling with us on this great journey. It is not an enemy attacking our ship. It is a passenger in the same cabin. We are all huddled together around the warmth of the sun. Earth, Mars, Jupiter, and the millions of asteroids. We are a family of matter, clinging together as we rush through the interstellar void. This perspective dissolves all fear. How can we be afraid of a stone that is traveling the same path we are? We are all falling through the galaxy together. The approach was just a slight shifting of seats in the cosmic vessel, a neighbor moving a little closer for a moment before settling back. As we conclude this journey, let the feeling of motion settle over you. Not a frantic motion, but a smooth, eternal glide. You are flying. You have always been flying. The chair you sit in, the bed you lie in, they are not still. They are part of the great caravan. You are safe inside the bubble of the solar system, protected by the sun's magnetic field, shielded by the breath of the solar wind. Outside, the stars of the galaxy stream past, too slow to see, but moving nonetheless. 1 minute ago. That minute is now gone. It is lost in the drift. It has been swallowed by the galactic year. Whatever worry you held at the beginning of this hour, let it go. Let it drop into the wake behind us. We are moving too fast to carry heavy things. Focus on the silence of the space between the stars. It is a clean silence, a pure silence. It is the silence of peace. The universe is functioning exactly as it should. The gears are turning smoothly. The gravity is holding. The light is shining. You do not need to do anything. You do not need to steer the planet. You do not need to push the asteroid. The laws of physics are carrying you. You are free to simply be, to simply breathe, to simply watch. The detection screen is blank. The data has been stored. The night is quiet. We are living inside a cosmic void, and we have noticed the beauty. We have noticed the order. We have noticed the safety. And in noticing, we have found our home. Drift on, traveler. The stars are watching over you, just as you watch over them. All is well, all is quiet, all is clear. Close your eyes for a moment and imagine the sensation of weight. We often take it for granted, the simple pull of the earth beneath our feet. It is a constant, a quiet companion that defines the rhythm of our lives. From the way our hearts beat to the way trees reach toward the sky, everything we know is calibrated to the strength of one gravity. But the universe is a vast and varied place, and the rules we consider absolute are often just one possibility among millions. Somewhere out there, orbiting a distant, steady sun, is a world that challenges everything we understand about the limits of life. A world where the pull of the ground is 3 times stronger than what you feel right now. This is a journey to a planet with 300% of Earth's gravity, a place of crushing pressure, strange beauty, and an enduring, quiet resilience. To understand this world, we must first understand the invisible hand that shapes it. Gravity is not just a force, it is the architect of existence. On Earth, we move with a certain lightness. We can jump, we can run, and our bones are light enough to allow us to stand tall. But on this heavy world, every movement would be a monumental effort. Imagine carrying 2 versions of yourself on your shoulders every second of every day. Every step would require the strength of an elite athlete. Your heart would have to work 3 times as hard just to push blood to your brain. On such a planet, the very concept of up becomes a challenge. Yet, as we look closer, we find that this is not a wasteland. It is not a place where life is impossible. Instead, it is a place where life has found a different way to be. This planet is a super Earth, a category of world we are only beginning to understand. It is larger than our home, more massive, and its grip on everything it touches is unrelenting. But within that grip there is stability. There is a thick, protective atmosphere. There is the possibility of liquid water. And where there is water and stability, there is the potential for a story to unfold. As we begin our descent toward this heavy world, the first thing we notice is the sky. It is not the pale blue we are used to. Because the gravity is so high, the atmosphere is pulled tightly against the surface, compressed into a dense, thick blanket. This high pressure changes the way light scatters. The sky might be a deep, bruised purple, or a rich, dark indigo, even at midday. The sun, perhaps a long-lived red dwarf, hangs low and steady, its light filtered through layers of gas that would feel more like water than air. As we drift downward, the sensation of weight begins to settle in. It is not a sudden blow, but a gradual, inevitable pressing. It is the feeling of being pulled home, but with a ferocity that demands respect. On this planet, the mountains do not reach for the stars. They are broad, low, and rounded, smoothed by the relentless tug of the planet's core. The valleys are deep and wide, carved by rivers that flow with a terrifying, heavy momentum. Here, the landscape is a testament to the power of mass. But why does such a world exist? In the early days of a solar system, dust and gas swirl around a young star. In some places, like our own, the material settles into small, rocky planets and large, distant giants. But in other systems, the middle ground is more common. A planet grows large enough to hold onto a massive amount of rock and metal, but not so large that it becomes a gas giant like Jupiter. It stays solid. It develops a crust. It holds onto its heat for billions of years. It becomes a super Earth. And because it has so much mass packed into its sphere, the gravity at its surface rises to levels that would crush a human being in minutes. And yet, if we could stand there, protected by technology or perhaps born of that very soil, we would see a world of profound stillness. There is a dignity in the heavy world. Things do not break easily here because they are built to last. The rocks are dense, the minerals packed tightly together. The very ground beneath us is a foundation unlike any other in the cosmos. It is a world of 300% gravity, and it is waiting to tell us its secrets. As we settle onto the surface of this massive world, we must adjust our senses to a new kind of environment. The air here is not the thin, fleeting substance we know on Earth. Because of the 300% gravity, the atmosphere is incredibly dense. At sea level, if we can call it that, the pressure would be equivalent to being deep underwater in Earth's oceans. To breathe this air would be like inhaling a thick mist, a physical presence that fills the lungs with a weight of its own. This density has a profound effect on the planet's climate and weather. On Earth, our atmosphere is dynamic, with winds that can reach hundreds of miles per hour. On this heavy planet, the air is too thick to move with such frantic energy. Instead, the weather is slow and deliberate. The winds are more like ocean currents, moving in vast, sluggish rivers of gas. They carry immense force, not because of their speed, but because of their mass. A gentle breeze on this world could knock over a stone pillar, pushing with the weight of a slow-moving tide. Because the atmosphere is so thick, it acts as a perfect thermal blanket. Heat from the planet's interior, kept warm for eons by the immense pressure of its own mass, is trapped and distributed evenly across the surface. There are no harsh winters here, no scorching deserts. The temperature is remarkably constant from the equator to the poles. It is a world of eternal heavy twilight, where the heat is a physical embrace, steady and unchanging. The light that reaches this surface is also transformed. Most super-Earths discovered so far orbit M-dwarf stars, also known as red dwarfs. These stars are smaller, cooler, and much longer lived than our Sun. They emit most of their energy in the infrared spectrum. Through the thick, compressed atmosphere, the light of a red dwarf would appear as a deep, ruby glow. It would not be the sharp, white-yellow glare we are used to. Instead, the world would be bathed in a soft, crimson radiance, casting long, soft shadows that never quite disappear. For any life that might evolve here, this light is a precious resource. On Earth, plants are green because they absorb blue and red light and reflect green. On a heavy world under a red sun, the colors of life would be vastly different. To capture the low-energy photons of a red dwarf, the equivalent of plants might be pitch black or deep purple, designed to absorb every scrap of energy that makes it through the thick clouds. Imagine a forest of low, sprawling organisms, their leaves, if you could call them that, wide and flat to catch the dim light, and thick and leathery to withstand the crushing air. The density of the air also changes the way sound travels. In a thick atmosphere, sound moves faster and carries much further. The heavy world is a world of deep, resonant echoes. The sound of a falling rock or a distant river would vibrate through the air like a low-pitched drum. Communication here would not be through high-pitched chirps or whistles, but through deep, subsonic rumbles that can be felt in the very ground. It is a world that hums with the vibration of its own existence. But the most striking feature of this environment remains the water. If this planet is habitable, it likely possesses vast, shallow oceans. Under 300% gravity, water behaves differently. It is pulled flat against the crust, filling every low-lying basin with a relentless efficiency. The waves on these oceans would not be the tall, crashing breakers of Earth. They would be low, heavy ripples, moving with a terrifying momentum. The pressure at the bottom of these seas would be enough to create exotic forms of ice, even at high temperatures, phases of water that only exist under the most extreme conditions. In these heavy seas, life would find its most stable sanctuary. Water provides buoyancy, a natural counter to the relentless pull of gravity. In the depths, the difference between 1G and 3G is less meaningful than it is on land. Here, The first ancestors of the heavy world might have begun their journey, drifting in the nutrient-rich high-pressure currents, protected from the radiation of their temperamental star by miles of dense air and water. The landscape itself tells a story of endurance. Because of the gravity, there are no tall trees reaching for the sky. Instead, the vegetation consists of low-lying mats and thick crystalline structures that hug the ground. They are built with reinforcements of silica or heavy metals, minerals that are abundant in the crust of such a massive planet. These organisms do not grow upward, they grow outward, claiming territory with a slow, grinding persistence. Even the geology is subdued. Volcanism on a heavy world is a different beast. Magma must fight against the immense weight of the crust to reach the surface. When it doesn't erupt in spectacular fountains. It flows out in thick, heavy sheets, creating vast plateaus of basalt that stretch for thousands of miles. The tectonic plates, if they exist, move with a glacial slowness, their movements dampened by the sheer mass of the rock above. It is a world that feels solid, permanent, and old. To inhabit a world of 300% gravity, life cannot simply be a stronger version of what we see on Earth. It must be fundamentally reimagined from the cellular level upward. Every biological system we know, from the way nutrients are transported to the way a body supports its own weight, is a direct response to the gravitational field it occupies. Consider first the skeleton. On Earth, our bones are made of a porous matrix of calcium and collagen. In a triple gravity environment, such a structure would be dangerously fragile. Life here would likely utilize much denser building materials. Imagine skeletons reinforced with carbon fibers or perhaps even metallic compounds scavenged from the rich, heavy soil. These bones would not be long and slender, they would be thick, short, and incredibly dense, more like the granite foundations of a building than the delicate limbs of a mammal. The muscles that move these heavy skeletons would need to be equally specialized. Movement would not be fast or explosive, but it would be relentless. A creature on this world might move with the slow, unstoppable grace of a tectonic plate, each step a calculated application of immense force. Perhaps the most significant challenge for life in high gravity is the circulatory system. On a planet with 300% gravity, the weight of the blood itself becomes a lethal problem. If a creature stood upright, the gravity would pull all its fluids into its lower extremities, causing the brain to starve of oxygen in seconds. To solve this, life on the heavy world might never stand up at all. Most creatures would likely be low-slung, with horizontal bodies that distribute their weight across many points of contact. Instead of 4 legs, imagine 6 or 8, thick and pillar-like, positioned to keep the heart and brain on the same level. For those rare organisms that do venture into a vertical posture, their hearts would need to be massive, multi-chambered pumps capable of generating pressures that would burst human veins. Their blood vessels would be reinforced with thick layers of smooth muscle and elastic tissue, acting as secondary pumps to keep the life-giving fluid moving against the crushing pull of the planet. Internal organs, too, would require suspension systems. In 3G, the liver, the stomach, and the intestines would be pulled downward with such force that they could tear away from their attachments. Life here would likely evolve thick, fibrous membranes to anchor every organ securely to the skeletal frame. The concept of soft tissue might not exist at all. Everything would be firm, resilient, and tightly packed. But even at the microscopic level, gravity makes its presence felt. The way a cell divides, the way proteins fold, and the way membranes transport ions are all influenced by the physical environment. In high gravity, sedimentation within the cell becomes a factor. To prevent the cell's internal machinery from settling at the bottom, the cytoplasm would likely be more viscous, a thick jelly that holds everything in place. The energy cost of simply existing would be significantly higher, meaning that life on this world would need to be incredibly efficient at capturing and storing energy. As we observe this ecosystem, we notice a profound sense of stillness. There is no frantic buzzing of insects, no sudden leaps of predators. Everything moves with a slow, deliberate cadence. Even the predators would be masters of patience and ambush. A hunter on this world doesn't chase its prey. It waits, blending into the heavy basaltic landscape until the perfect moment to exert a single, crushing burst of force. In this environment, the concept of falling is the ultimate fear. On Earth, a fall is a mishap. On a 300% gravity world, it is a terminal event. Every creature would have an instinctive, deep-seated sense of balance. Their nervous systems would be hardwired to maintain a stable center of gravity at all times. This would lead to a culture of caution, a world where the bold do not survive, but the steady and the sturdy thrive. If we imagine that intelligence could arise on such a world, we must reconsider what progress and technology would look like. A civilization born under the weight of 3 gravities would face challenges that we can barely comprehend. The first and perhaps most daunting hurdle is the gravity trap. On Earth, we have reached the stars because our planet's gravity is weak enough that we can build rockets to escape it. But on a super-Earth with 300% gravity, the energy required to reach orbit is exponentially higher. To launch a rocket from the surface of this heavy world would require an amount of fuel that is almost physically impossible to carry. For the inhabitants of this world, the sky is not a frontier, it is a beautiful, unreachable ceiling. This enforced groundedness would shape their entire worldview. Their curiosity would be directed toward the depths of their own planet. They would be a civilization of geologists and materials, scientists, masters of high-pressure engineering and deep-crust exploration. Their architecture would reflect this. There would be no skyscrapers. Their cities would be built downward, carved into the dense, stable bedrock. To build up is to fight gravity. To build down is to use it. Communication for such a species would be a fascinating study. In a dense atmosphere where sound moves quickly and carries immense energy, their language might be a symphony of low-frequency rumbles and subsonic vibrations. They wouldn't need to see each other to talk. They could feel each other's presence through the ground, a tactile connection that spans miles. Their sense of hearing would be vastly superior to ours, capable of detecting the subtle shifts in the planet's crust or the approach of a distant storm long before it arrived. Their philosophy might reverse our own values. Stability, depth, and endurance would be the primary virtues. Their myths might tell of the great core, the source of all weight and life, and their heaven might be a place of perfect, unmoving stillness deep within the earth. They would be a people of profound patience, understanding that true change takes eons. As we move deeper into the narrative, we must leave behind the ruby-tinted twilight of the surface and descend into the crust itself. On a planet with 300% gravity, the surface is merely a thin, compressed interface. The true heart of the planet's habitability may lie beneath the basalt, in a vast, interconnected realm of high-pressure liquid and mineral-rich heat. Because the gravity is so intense, the pressure increases much faster as you descend into the ground than it does on Earth. Just a few miles down, the pressure is already equivalent to the deepest trenches of our oceans. Under these conditions, the chemistry of life begins to shift. Water remains liquid at much higher temperatures. Life here does not depend on the dim light of a red dwarf. It depends on the slow, rhythmic cooling of the planet's core. Imagine a network of veins stretching through the dense bedrock fissures filled with superheated, mineral-saturated fluids. In these veins, life forms that look more like crystals grow in slow, geometric patterns. These are the lithotrophs, organisms that eat the very rock they cling to. This subterranean ecosystem is the foundation of the planet's stability. While the surface might be buffeted by the slow winds, the deep crust remains unchanged for eons. In the deep, the concept of time is even more dilated. Without the cycle of day and night, life follows the breathing of the planet. The slow expansion and contraction of the crust as it tides under the influence of the sun. The organisms here are masters of the long game. They are built to endure, to wait, and to persist. They are the living embodiment of the heavy world's core philosophy. That which is deepest is most real. As we look toward the furthest reaches of time, the significance of the 300% gravity world becomes even more profound. We are living in the stelliferous era, but eventually the bright stars will fade. In this cold, dark future, the red dwarfs and their super-Earths will be the last bastions of light and life. Because a red dwarf can burn for trillions of years, a planet with its massive internal heat reserves and stable atmosphere becomes the ultimate refuge. When every other world in the galaxy has frozen solid, the heavy world will still be warm. Imagine a universe 10 trillion years from now. The stars are few and far between, but around a lonely red dwarf, a super-Earth continues its slow, heavy rotation. Its inhabitants are the final observers of the cosmos. To them, the entire history of the universe, the era of the bright stars, would be ancient myth. They would be the keepers of the universal memory. The 300% gravity, which once seemed like a crushing burden, is now revealed as the greatest gift. It is the mass that allowed the planet to hold onto its heat and keep its atmosphere from leaking into the void. The gravity trap was not a prison. It was a sanctuary. It was the universe's way of ensuring that something, somewhere, would survive until the very end. The heavy world is a bridge between the chaotic beginning and the cold conclusion. It is a testament to the fact that life is not a fleeting accident, but a persistent force. We return now to our own time, to our own light gravity and our own brief, bright sun. But we carry with us the vision of the heavy world. We see it out there, in the dark, a world of 300% gravity, waiting for its turn to be the center of the universe. It is a world of incredible strength and incredible patience. It is the eternal cradle, the final refuge, and the ultimate home. In the end, the story of the heavy world is our story too. It is the story of how mass creates meaning and how life will always find a way to endure. We are all passengers on these rotating spheres, held fast by the invisible hand of gravity. And in the heart of the heavy world, we find the reassurance we need, that no matter how dark the universe becomes, as long as there is mass and the will to persist, the story will continue. The heavy world remains grounded, solid, eternal.